Hello, my name is Marianne Perez and my partner is
Jaxari Castañon. DTMF or dual tone multi-frequency is what is used in telephone systems. The way this works is that a digidial will have two tones played of different frequencies based on the row and column they are located at. In part 1, we learned the equation that corresponds to a pure tone. We also learned how to read and write wave files and learned about other important terms that would be extremely important for the rest of this project.
We decided to start this project on November 30th, which was on Monday, giving 1 day and a half to complete each part. My partner Jaxari began the first part and explained to me to go ahead and start part 2. So for the first part, the objective was to create WAV files with Python and store them into the computer to use them later on, to listen to them or import them to Python. As we were given the formula of a tone, it helped us develop the tone itself with some pieces of information, such as the amplitude, frequency, and a random phase shift. On the first part of the project, it was explained to us how we were going to solve almost all of the tasks. However, we had to look up some of the pieces of information. For this task, my partner looked up different octaves of piano notes to use them as the frequencies. This will be used later on in task 2 to graph our C3, C4, and C5 tones. We already had the amplitude given and the phase shift we were to decide, so we used pi over 2. Also, we were given the sampling frequency and the beats. For the time, we gave it 1 second duration, and then we used the tone formula with our piano notes, frequencies, to create their tones. After that, we had to convert the tones to integers in 16-bit format with the formula 2 to the bits minus 1 times our original y, respectively. And finally, we graphed it to see the relationship. What we noticed how they were related was that all of them have the same amplitude, that the higher the octave of C that the note is, the more frequent the signals occur, and the lower the wavelength, while the lower the octave of C that the note is, the less frequent the signals occur, and the higher the wavelength. Also that some tones interfere at certain times. Then we created the WAV files for each tone in task 3, and in task 4, we graphed the first 10 milliseconds of the file we were given, and we agreed that the frequency made sense because of how the graphs of the piano notes compared to the tone given, and we noticed it was similar to the C4 piano tone. Then we determined its frequency, and it lied within the range 270 and 300 Hz. Part 2 started a little bit more challenging as the project went along. We were given a row column assignment of frequencies for digits from 0 to 9, and also asterisks and pawn. The first task, I found it very challenging and difficult to understand. After I understood, I was finally able to define each digit using the formula given for tones with 2 frequencies and the same amplitude. We were given the amplitude, phase shift, sampling frequency, and bits, also the time, and for the frequencies we had to use both that corresponded to each digit, as we were given in the row column assignment. But for the phase shift, we had to give random values to each digit, so I used the random choice function. After defining each digit, the task stated that we had to create tones for each of them separately and listen to them. For task 2, using the sampling frequency and each of the tones, I graphed the first 10 milliseconds of each digit separately and saw their differences to compare each other. For task 3, we had to choose a single digit and generate it 5 times to see if there was any difference by listening to the respective 5 different tones created. So I decided to use digit 0. Then in task 4, I graphed them and noticed that there was no difference at all in those sounds, nor in the graph, which we later realized it would be a mistake that will be explained later. The last part was very challenging for me. I was not able to do it, so my partner helped me. For the last part, we discussed how we wanted to store the signals, and I came up with the idea, with the help of the lectures given in class, to create a data frame containing all the signals. However, it was too big that CoCalc said it ran out of storage, and my partner downloaded Anaconda 2020 to her computer to see if it worked like that, and it did.
Creating this data frame is when the course topics of loops and conditional statements came in handy. Since there were 10,000 random signals that had to be generated, we wanted to use a way to do this as effectively as possible. So we used a for loop to repeat generating a signal 10,000 times. Inside this loop, a random digit would be generated, and if and elif statements would help add an array of the signals generated to a list. Also, the digit and frequencies to which they corresponded to would be also added to separate lists. As mentioned previously, we use these arrays to create a data frame and then make it into a CSV file. After looking at the comments from Dr. Karp on Blackboard, we knew there were some changes we had to make before continuing to part 3. The signals in our database were all identical, which was not right. The equations were not generating random phase shifts. This is also why the graphs looked identical in part 2. We looked back and replaced random.choice with np.randomChoice. This appropriately made different signals for our digits in our database. Part 3 is where we practice obtaining the digit from the signals from our database. My teammate and I came up with many ideas, but we decided the best one would be to create a function where the digit is returned based on a given row of a signal in our database. The digit would be obtained from the column digit. The percentage of correct determination is also returned, as can be seen here. When working with task 5, we were not quite sure how to implement our idea, but I came up with the idea to add the noise to the data for each signal and graph the original signal with and without noise. From here we could compare and see that the shapes are almost similar, but the amplitudes are not quite equal to each other. Continuing to part 4, we made the decision to use the FFT method provided. The goal here was to obtain the 10 digits styled in each WAV file. Again, we used similar methods to our data frame approach in part 2 by using for loops and conditional statements. We created 10 for loops where each loop had different sections of 1,000 milliseconds of a WAV file. The if statements would help look for the frequencies at which the largest amplitude in the magnitude spectrum occurred. If they matched with the frequencies of a digit, then the corresponding digit would be added to a list. The first trouble we had here was that our if statements were not working. We looked more in depth and printed the function .argmax for the first second of each WAV file, which is in our first loop. The frequencies that were given were not the same as the one given in part 2. For example, the 697 Hz for the first row was given as 696 Hz, and the 852 Hz was given as 848 Hz. We made the changes accordingly, and our for loop worked. The only issue we noticed is that the lengths for certain digits were not equal. For example, we would get 114 values returned for the third digit list, but only 81 for the seventh digit list. At this point, we were not able to find what was wrong with our code. We decided to make the data frame, and where any missing values would be given NaN. Then we turned that into an Excel file, as can be seen here.